Thank you. My name is Alexios Papalexopoulos. I'm the CEO and founder of Eco International. We're market designers for 20 years now. We built ISO and TSO markets, mainly Nodal markets, but also European type of markets. My co-authors are Frowd of Eco International and Professor Alexios Birbas from the University of Patras in Greece. The topic today that I'll present is the development of an organized local market, local energy market at the DSO level, but nodal market, which is very important for us. So we produce locational marginal prices with full representation of asymmetric, unbalanced distribution networks. First, I'll present the evolution of the markets. This is extremely important to understand how we're moving from TSO to DSO markets and how this is a result of the DR massive penetration in the market. I'll present a very brief formulation. The details are in the paper, the solution method we're following, some open issues and some applications I have in the paper, and I will close with a necessary framework for the TSO-DSO coordination. Okay, first, what drives this evolution is basically the DR proliferation. There are many market forces for that. One is the bottom-up demand and adoption. Basically, the customers want that. All types of customers, residential, commercial, and industrial customers, they want flexibility to manage their energy. They want to participate in wholesale markets, individually or through aggregators. Also, there's a need for grids now to become more resilient for various reasons. I have included here the superstorm Sandy in New York 3-4 years ago. So we're moving towards developing microgrids. Furthermore, cities and counties now at regions want to explore synergies for municipal services. Also, there's a top-down policy directive. Policymakers realize that DRs can support environmental goals. But most importantly, now that all these technologies now, they get much cheaper, they are much more powerful. So there are all these factors are lining up for the massive penetration of DRs. This changes the way we organize markets. We have developed markets in about 15 countries in North and South America, Western and Eastern Europe, and Asia. All our focus over the last 15, 20 years is in the development of the top market here for the system operators, the market operators, the TSO markets. But now with the DRs, we see the evolution of DSO markets, or how we call it local energy markets, LEM, local energy markets, where DR participate in those markets, DRs, directly themselves or through aggregators. Many countries now, they have the legal framework for DR aggregators, or the end-use customers can participate. The reason this is a very important slide is if I'm a DR aggregator, let's say a solar plus storage, and I'm connected to the distribution system, I should have the flexibility to participate in a local market or directly in the TSO market or support customer needs behind the meter. I'll talk about this. So we're talking about a hierarchical structure of markets, 3 markets, wholesale markets, distribution markets, and markets behind the meter. As I said, what makes this possible is the IoT revolution. In the past, on the left here in the lower left, we're talking about wireless controllers to control individual devices in buildings, smart buildings, home management systems. But now we have electric cars, we have smart appliances, we have rooftop solar, storage, all these devices now, electric cars, are all connected to the cloud, that they create capacity, the capacity that can be split in tiers in different attributes, different levels of flexibility that can participate in retail and wholesale markets. So the framework that is evolving actually worldwide, I would say, is a multi-market participation. And as you see here, the 3 circles, wholesale markets on the lower left, distribution markets on the lower right, markets behind the meter, customer markets. Next to each circle, I have certain products and services that those markets procure. I don't need to go into detail. You're probably aware of some of these products. That's what we do over the last 20 years. We develop algorithms and platforms to clear those markets. Mainly our work has been on wholesale markets with ancillary services, energy and capacity products, but now we have markets on distribution that we want, and our vision is to have also nodal markets in distribution to solve distribution problems, and furthermore harness the maximum value of location of DRs, because location matters. And on top, I have certain applications for behind the meter. So what we have done with the distribution market we developed for a country in Europe is basically three markets: a day-ahead market, an adjustment market. The day-ahead market operates from the previous day. The closure of the day-ahead markets at 10 a.m. in the morning, then operates on an hourly basis for the following day, the active day. It can also go for day 2 and day 3. We have a time horizon basically of the active day, 24 hours. The time intervals is half an hour. So we solve for 48 intervals for the next day. We're getting offers at 10 a.m. in the morning of the previous day. Those offers are simple price quantity offers, but also can be complex offers or block offers, or the offers that the European markets allow, linked offers, or any, also bilateral deals. Okay, so in real time also, we have a 5-minute product that we produce for the next hour. The market closes at T-minus 7.5 for the intervals 0 to 5. So we have 5-minute intervals consistent with the wholesale markets. The gate closure is at T-minus 15, and we repeat that as the window moves forward. So what we produce with that is distribution LMPs. This is very important. We produce locational marginal prices all the way down to the feeder at the customer level, okay? Not all, the same thing we do for wholesale markets in the US for the transmission system, but now we produce these DLMPs all the way down to the distribution level. Now, methodology-wise, what do we use? We deploy the same methods we use for the transmission system for the TSOs and DSO markets. Of course, there are major differences. So we overlay in economic models based on mixed integer linear program where offers and bids are housed. We overlay that on the top of the distribution power flow. The distribution power flow is three-phase. Distribution power flow is asymmetric. We use real distribution power flow methods, AC power flow methods. Offers and bids are coming in through the DR operators. So we deal with any type of distribution markets, asymmetric distribution networks, meshed, radial. So because it's three-phased, we produce for every node 3 DLMPs, 3 prices, distribution locational prices, 1 for each node. It's very important to note that the price of the ISO or the TSO of the substation is an input to the distribution algorithm, okay? So how it works, simply, as you see in this figure here, we start with an unsolved, unbalanced AC distribution flow. We check all the line transformer flows against limits. If there are overloads, we linearize those constraints. We come up with shift factors using the factorized Y bus metrics, and the linearized constraints are being passed to the mixed integer programming, and we repeat this process till we solve. When there's no overloads, we'll calculate the LMPs. And the paper describes all these things, how we produce the LMPs using the shadow price of the balance constraints and also the shift factors and the shadow cost of the congestion. This tells you how we do this. On the left, we have the economics, the mixture programming. On the right, we have a distribution power flow, one every half hour, 48 power flows. We repeat, we linearize the constraints with the PTDFs, the power transfer distribution factors. We have one single power balance for every local market. The math is in the paper, no need to go into detail. We have a power balance constraint. We take into account the transfers from the transmission network. We take into account all the offers and bids. We linearize all the branch constraints. We also have ancillary services constraints. All these things feed into the platform, and that's how it's solved iteratively to produce distribution, locational marginal prices all the way down to the feeder. We have problems. The problems are basically availability of data. We get data from GIS systems or DMS systems, but we need metering data for the real-time market, depending if it's a 5-minute market or a 50-minute market. Availability of data is important. Also data that may belong to different loads, different retailers for participating loads that participate with demand response, or non-participating loads. For non-participating loads, we use load profiles. There is a problem with the volume of data, massive volume of data. Below, I think 33 kV in most countries, the systems are radial, but still asymmetric. A big problem is the behavior of Nodal LMPs. Of course, if there is no massive penetration, we have scarcity issues. So scarcity pricing and mitigation issues are very important for us. We are, developing mitigation plans and scarcity pricing for TSO markets for a long, long time. So we try to apply similar principles in distribution. There is a lot of activity in the US mainly that they tend to subjugate the distribution markets to wholesale markets, meaning, okay, we don't need to develop a distribution market. Let's use the transmission market. The prices in transmission, we are augmenting with a scalar to take into account the cost of distribution constraints plus cost of losses. And that gives you the cost for distribution in every bus. We don't like that. We don't approve that. We're market people. Those markets need to be developed independently, and of course they need to be coordinated, of course. There are many applications of that. One main application is the scheduling of DRs.
Minutes, scheduling. Alex, please.
Say it again?
2 minutes.
Okay, no problem. So one problem is the feeder reconfiguration. When the DR offers are not sufficient to solve grid problems, congestion problems on the distribution grid, then we utilize what we call optimal reconfiguration with 0-1 optimal variables that the mixture programming solves. So we come up with optimal reconfiguration of the feeders to solve congestion problems in the distribution grid. I will close with this important slide. Coordination is important. We have a whole section in the paper. Coordination needs to happen in all levels. We don't believe that the TSO will take over the distribution. It's not going to happen for many reasons, regulatory and technical. Also, we don't like the DSO to subjugate all the DRs. The DRs need to have unfettered participation in the TSO markets. So we need coordination in all levels. We need for voltage support, grid balancing, black start protection, islanding. So we need to take into account in all markets, day-ahead markets, and real-time markets to do that coordination. Last slide, key message. The action has moved from wholesale markets to distribution. All the new generation is in distribution, renewable energy. We're moving to a zero marginal cost markets now with renewables. At local energy markets, DRs markets are emerging. The regulatory framework is evolving. We need unfettered participation in this hierarchical multi-tier energy market I presented in order to maximize the value of DRs to the grid. We don't believe in DR subsidies. They need to be phased out now. And location is important. In the US, all location, we have nodal markets, so transmission grids are fully represented in the clearing to produce prices to reflect congestion and losses. When you do the same thing in distribution, in order to harness the maximum value of DRs to include distribution constraints and to produce prices to reflect locational effects. Thank you.
Thank you a lot, Alex. Okay, we have time for some answer. Very last. One from Dan. Can you have a look on the question and answer? We have, can you please expand on the distribution network reconfiguration? If it's going to impact on locational marginal price?
Yeah, on the reconfiguration, one thing we realized, this is not an academic exercise, okay? This is development for a real system with thousands and thousands of nodes hanging from feeders with each feeder 400, 500 nodes. One thing we realize is that many feeders don't have a lot of DRs, okay? So scarcity is important. To solve the congestion problems, distribution and other problems, we need a lot of DRs, we need a lot of offers. We don't have that in many places. So we need to expand the markets gradually. So if we run out of DR offers to clear the market and solve the grid problems, then our last resort is to do reconfiguration. In other words, to do what we call feeder switching. Feeder switching, if you talk to distribution operators today, there's no market. Every distribution company operates a distribution system. They adjust the feeder loads, they do reconfiguration, but on a manual way. So they develop distribution plans. Those methods have not worked well when we have multiple layer transfers, or we have a lot of DRs now in conjunction with load transfers. So we have, based on the requests from clients, we have updated the platform to develop optimal switching plans in combination with DR market-based scheduling based on offers. So basically, what we do, we apply penalty for those variables, like the variables are 0 to 1, they are integer variables. We apply penalty, which are higher level offers. So if we exhaust the DR offers to clear the problem, then we rely on the optimal reconfiguration. I don't have examples to show here, but we have a lot of real life examples how the optimal reconfiguration works. When we exhaust the market-based offers for DRs, then we rely in optimal switching plans to solve distribution problems by really solving a mixed integer linear program that using integer variables with some high penalties that are utilized after we exhaust the offers from the market.
No, it's clear from the technical point of view of solving the problem. Maybe Dan was raising how to deal with the locational price, taking consideration fairness about the reconfiguration. One more question was about distribution voltage constraints were considered, voltage constraints?
Yeah, we have all the modeling in the paper. If you take a look at it, we include constraints, voltage constraints.
Thank you, Alex. I see one hand raised from Tanovek. I ask all of you who has questions to use question and answer. It could be more effective and can be shared among all. So I think we can thank you again.